All right, we're going to try that last part again. Imagine we have this y equals g of x function, and what you can notice here is that if we look at our first condition, we notice that g of x is not continuous. And we also can notice if we look at the second condition, AB is open. So we can't really use the extreme value theorem. It doesn't really apply. It doesn't tell us anything. If we look at the actual graph here, though, what we do see is that we do have an absolute max right here at C. So we have an absolute max of G of C at x equals C. And we have no absolute min. Because if I look at my potential options for my absolute min, it would probably be this one right here. But A is not included. Alrighty. So keep in mind what I said before, right before the last video dropped off. The extreme value theorem guarantees an absolute max and an absolute min exist. It does not mean that an absolute extrema does not exist because I can't use the extreme value theorem. Okay, so this is an example of where I do have an absolute extrema, but EVT doesn't tell us anything. Alrighty, okay. So if I take a look at this y equals f of x defined on a closed interval, so here I have a y equals f of x on a closed interval AB, right? So here, if I look at this, f of x is continuous. I can follow it, right, with my pencil without lifting it. If I look at the limits at every single point, they exist. And my interval is closed. It's a really horrible bracket. Sorry. There we go. All right. So that means by the extreme value theorem, we know that an absolute max and an absolute min exist. Alrighty. So if we look here, the absolute maximum is going to be right here. So we can say there's an absolute max. I don't know where that came from. Of f of s at x equals s, right? The absolute maximum, there's no greater value of f on AB. It's also a local maximum. Local maximums are coming back. You'll notice there's a local maximum right here. There's a local maximum right here. Our absolute minimum is right over here at f of b. So we have an absolute min of f of b at x equals b. And you'll also notice that there's two other local minimums right over here that are smaller in the interval, but they're not, their values of f of r and f of p are not as low as what it is for f of b. Okay, so those are local minimums. You probably remember those also from algebra. So if we talk about local minimum and maximum values, suppose C is an interior point of some interval I on which f is defined. If f of C is greater than f of x for all x in I, then f of C is a local maximum value of f. And if f of C is less than or equal to f of x on all x in I, then f of C is a local minimum value of f of x. Note, in this text, we say local minimum and maximums occur only at interior points. So as you're doing your homework, note this. So not at the end point, okay? So basically what they say is end points on an interval are not local maximums, but they can be, and often are, absolute max or absolute mins. Okay. So they're considered absolute extrema at the endpoints, but your book does not define them as local extrema. Alrighty? Okay. So let's take a look at the next page. If we want to locate the various maxima and minima, so like here, let's say we want to locate, well, the extrema. All right. So first let's consider the extreme value theorem. We notice this is continuous. And notice that we're on a closed interval. So we know we're going to have an absolute maximum. So we know that an absolute maximum and an absolute minimum exist. So if we look at the highest peak that we can see, I would probably argue that we have an absolute maximum at Q here. So I'm going to say there's an absolute max of f of q at x equal to q. I'm going to say that it appears, from what I can see, there's an absolute minimum of f of p at x equal to p. Now, if I want to look at other local maxes or mins, I could say there's also local maxes. One would be at of f of a at x equals to a. Obviously, f of q is also, it's not only an absolute, it's also a local max at x equals q. And then the last one that I'm going to pick is f of s at x equal to f. Okay, so we have 3 local maximums And then if we look at our local minimums, what I'm finding here is we have a local min at our absolute min, so f of p at x equal to p. I have a minimum right here at f of r at x equal to r. And I finally have the last one, the local minimum f of b at x equal to b. Okay? So we can see the local mins and maxes appear at points on the open interval AB where the derivative of f is equal to 0. So if we take a look at this, let me change colors real quick. What you can see is, well, if this was straight, what you would see is, right there we have a nice horizontal line. Right here we would have a nice horizontal line. You can see that the derivative is 0 or it fails to exist. So if we look at this point right here, down here by P, what I have is a slope as I approach from this side that looks like this for my tangent, right? And the slope as I come in from this side looks like, well, we'll try and grab that line, looks kind of like that. So they're kind of crisscrossing each other. So here, f prime of p does not exist. So what we are actually seeing here is that the local maxes and minimums I think I lost a letter. Minimums occur when, maybe this a little bit bigger, when f prime of x, for whatever x we're looking at, equals 0, or when f prime of x does not exist. Oh, that was nice of it. Does not exist. Okay. So the reason, if we want to take a closer look at that, as to why we have it happen when we have a slope equal to 0, and we've kind of talked about this before in class. If you look at our maximum, what you can see is the slope of the secant line here as we get closer and closer. Here, it's increasing at a larger, for this one, right here, it's increasing at a larger slope as we get closer and closer and closer to our A value, where our maximum is here, or I think this is supposed to say C, to our C value. What you see is that the curve is getting flatter and flatter and flatter. When we reach C, the slope of the curve is 0, okay, of the tangent, and then we begin decreasing. Okay, so notice that the slopes of the secant lines over here on this side are greater than 0, and the slopes of the secant lines over here on this side are less than 0. And that's going to be the same for the tangent lines of any point too. So the slopes of the tangent lines over here, lines would also be greater than 0 on this side, and the slopes of the tangent lines on this side are going to be less than 0. Okay? So you can see how it switches from an increasing slope to a decreasing slope. All right? So that leads us to our next thing, which actually I think I was trying to grab off of when I found videos for you guys. The local extreme value theorem. If f has a local minimum or local maximum value at c, then f and f prime of c exists, then f prime, the derivative of f at c, is equal to 0. Okay? We can use this information to define what we call a critical point. This is also sometimes called a, well, not always, not in this case. So we're just going to call them critical points right now. One of them is called a stationary point sometimes, which you'll see. An interior point C of the domain of f at which f prime of C equals 0 or f prime fails to exist. So the derivative of f at C is 0 or the derivative of f at C fails to exist is called a critical point of f. These are points where we want to keep an eye out for what's happening, okay? So here, if you're looking at this part, you're either looking at something like a discontinuity, like a jump in your graph with a piecewise function, or you're looking at what I'd call, I guess, a pointy point. On the graph, right? So if we look back to the 1, 2, a few up, if we look at that area there with P, you can see you kind of have a little point there. Alrighty, so we have a pointy point in the graph. Alright, so if we come back down here to where we were, figure 4.8, A and B, you'll notice we have a local maximum at C, which they label right this time, where the derivative of f at C does not exist. Okay, so this is a local minimum. The local minimum's here. Okay, so we have a local minimum that's down lower. And f prime of C here does not exist. So we have a discontinuity where we just have a point that's somewhere else. This is not, to me, this one right here is not a normal case. It's not something you see that often in everyday life. So, if we look at the one next to it, this is much more common. There's a local maximum at C where the derivative of f does not exist because there's a pointy part there, right? So the slope on one side is increasing at a constant rate, and the slope on the other side is decreasing at what looks like maybe an exponential fall off. I apologize. But we have definitely a absolute maximum or a local maximum right there. Okay.